So when we talk about decarbonization, we're talking about replacing fossil fuel combustion-based heat systems with heat from the deep subsurface.
Below 9,400 feet deep, there is the basement rock, which is also a very good candidate for a geothermal reservoir. The challenge here from a drilling perspective is that it's a highly heterogeneous rock, a very anisotropic rock, a rock that has discontinuities at multiple scales that we don't completely understand from a mechanistic point of view.
To fully implement the deep direct use, I think there's three main factors that will guide our decision making. One of them is the temperature, what's going to be there all long term, and the flow rate, and the long-term sustainability.
Welcome to Geothermal Unleashed, where we're going to explore the cutting edge of geothermal energy. I'm Elizabeth Cambry from the Burak New Energies team, and I'm here to help educate and document geothermal's rise in the global energy transition. I am thrilled to welcome our guest today from Cornell University, and we're going to be discussing three general topics. So we're going to talk about Cornell's decision to pursue deep district geothermal. We're going to talk about Cornell University's Borehole Observatory, and then we're going to talk about what it's like executing a deep drilling project in an urban environment. Joining me today is Wayne Bezner-Kerr. He's the Earth Source Heat Program Manager. We have Chloe Arson, who is the Professor of Earth and Atmospheric Sciences, and then Burak Erdinc, the Earth Source Heat Geoscientist. So welcome, everyone. And to start, I would like to invite each of you to introduce yourselves and then tell the listeners the role that you play at Cornell with this geothermal project. And so, Wayne, why don't we start with you?
Sure. Glad to be here. Thank you for the invitation to talk to our people, so to speak. My name is Wayne Bezner-Kerr. I'm at Cornell now for about 2.5 years in the role of the Earth Source Heat Program Manager. And Earth Source Heat is the name we have on campus for an attempt to build a deep direct use geothermal system and replace a fossil fuel fired district energy system.
Wonderful. Thank you. All right, why don't we hop over to Burak?
So, hello, everyone. My role as a geoscientist is collecting the data and also planning the data and the monitoring for the upcoming projects. So I'm supporting in many ways Wayne, but at the same time I'm sitting between the academia and also the third parties and everybody that's involved, try to link everybody together. So I'm kind of like a bridge, but at the same time, I'm supporting everybody in many different levels.
Wonderful. Well, thank you for joining us. And then Chloe, do you want to introduce yourself?
Yes, thank you, Elizabeth, for the invitation. I am a professor in Earth and Atmospheric Sciences at Cornell. I joined the university in 2023 after some years at Georgia Tech on the faculty. I am an expert in computational geomechanics, which is essentially the numerical modeling of rock masses and fractures. And I'm passionate about coupled processes. I got involved very early on with ESH, in fact, pretty much as soon as I joined Cornell. And my contribution to the overall effort is being the bridge between the engineering people on campus and the faculty. And when I talk about the faculty, I'm in fact more referring to the academic scene in general, not only in engineering, but also in other disciplines, as I'm sure we'll have time to talk about it later on in the podcast. So I can explain to you a little bit more what that entails. But it's very multidisciplinary and it is tailored towards research and education.
Wonderful. Well, thank you, everybody. So why don't we get kicked off, and we'll start first with talking about Cornell's decision to pursue deep district geothermal. And Wayne, I'm going to start with you. Do you want to give us a little background and speak about Cornell's decarbonization goals and then the timeline as well?
Sure. So Cornell, like many educational and other institutions, has an institutional goal of decarbonizing our operation. And being a Northeastern university, when we talk about decarbonization, a huge amount of the energy that we need to decarbonize is energy associated with heating our campus. So if you were able to look out my window behind me, you'd see that there's a large combined heat and power plant that is connected to a district energy system, which is currently supplying heat through steam to about 13 million square feet of building and infrastructure space. And that supports all sorts of operations, everything from where people live in dormitories to where people eat to where people go to class, and a lot of research and laboratory space, which is very energy intensive. Anytime that you have a building that has a single fume hood, you know that you're going through a lot of heat because of the air changes associated with keeping that environment safe for its occupants. We're also sucking a lot of heat out of it. So when we talk about decarbonization, we're talking about replacing fossil fuel combustion based heat systems with heat from the deep subsurface.
Okay, great. So what is deep direct use geothermal energy, and how does it have the potential to supply district heating systems effectively?
Really great question. And I think it pays probably to define what we mean when we talk about a district energy system. So Cornell is built like a lot of hospitals are built. Many college campuses, military bases, parts of some large American cities is very common in Europe. And what I mean is we have a central source of energy that makes electricity, it makes heat, it provides chilled water, provides potable water, and it is responsible for circulating and distributing so that any point in the attached system that requires a service can obtain it when it needs it in the amount that is required. Right now, we're using natural gas sources to make steam, and we're piping that steam around the campus. We want to replace that steam distribution with heat from a deep geothermal well complex, but that's kind of a multi-stage process because geothermal wells in our geology are really bad at producing steam. They're great at producing hot water. So the first step of this process is to convert our campus distribution to a hot water distribution system. And then that gives us tremendous flexibility to explore lots of different options. The most attractive option, we can talk about some of these others, is deep direct use. What do we mean by deep direct use of a geothermal system? We mean taking hot fluid from the subsurface and stripping the heat out of it via a heat exchanger and then recycling it back into the earth. And we say it's direct use because we're not going through an intermediate electricity generation step like most of the high-profile geothermal projects that are really exciting and are getting a lot of well-earned attention these days.
So
I'll just say before I move on that one of the things that's so attractive about deep direct use is there's a lot of geology in North America where we have access to hot water temperatures. We don't have access to the really high temperatures that makes electricity generation efficient. If we were to generate electricity in the temperature range that where we're located, we'd be at, mid-single digit efficiency. Whereas if we use it for district heating, we can be probably 75% efficient. We can be dramatically more effective in how we utilize the resources available to us.
And that makes sense. So what were the key factors that led Cornell to pursue deep direct use over other renewable heat options?
Some of them are personnel. We were very fortunate. We attracted an alum of Cornell University back to Cornell as a professor. That was Professor Jefferson Tester, who has had a very prominent role in the promotion and the distribution of enthusiasm and the ongoing support for research for geothermal energy across North America. He came back to Cornell about 15 years ago, in part because the Cornell senior administration had committed to decarbonizing the campus. And Jeff is a chemical engineer, but he's really an energy systems expert with a long engagement in geothermal. And he saw the Cornell campus as a fantastic laboratory, classroom, engineering demonstration project, and research opportunity. So that's a big part of it. The other part is that we did have that pre-existing commitment to decarbonize. And so Cornell takes its responsibility as a research and education hub really seriously. And it sort of asks the question, well, what does it mean to decarbonize when everybody's watching how you do it? And pursuing geothermal energy is one way that we can execute our responsibility in the community to be a leader.
So how does deep direct use compare to other renewable heat options in terms of efficiency and sustainability?
The efficiency question needs to be answered by a functioning system. So we'll have to come back and have another follow-up interview, hopefully in 2 years, and we can answer that with some numbers. From a modeling point of view, it should be able to outperform any other non-combustion-based alternative. The closest competitor, I would say, the one that's most widely adopted would be the shallow geoexchange or shallow geothermal system, which could be implemented on a district level as well. And that's a system that's well established in many parts of the world, especially in Europe. That would be a pretty disruptive system should we implement it on campus because of the large number of shallow boreholes that would have to be drilled. We'd be talking about thousands and thousands of shallow boreholes required to carry our heating load. There's significant inefficiencies that would come with that as well because Cornell operates a globally famous chilled water production system, which is sort of the corollary of earth source heat. We call it lake source cooling. We have a fantastically efficient lake source cooling system, which rejects heat to the deep water of the lake. If we were to move to a shallow geoexchange system, the annual balancing of the borehole exchange field would require turning down lake source cooling and giving up its very, very, very high efficiencies. So there'd be a net increase in energy use, which is a net increase in emissions associated with operating the system. Deep direct use geothermal has the potential to be a game-changing synergy with lake source cooling.
So were there any significant challenges or drawbacks with other renewable heat options that made deep direct use a more viable choice for Cornell?
Yeah, I would say that any system is a combination of benefits and drawbacks. And I don't want to suggest that Cornell has some sort of magic bullet that solves all problems without having any costs or penalties. It's not like that. That's not how engineering works. But other systems, whether we looked at ground source heat pumps or some sort of hybrid combination of electric boilers, ground source heat pumps, supplementary air source heat pumps, a variety of storage media, they all ended up with higher system energy use, which means higher emissions associated with providing that energy.
So are there any technical or logistical challenges in implementing deep direct use for district heating systems?
I'll let Burak talk more about the complexity of some of the drilling and exploration environment from a campus engineering point of view. It's a major undertaking. A campus designed to operate on steam requires a lot of work, a lot of effort to convert it to hot water distribution. That happens both underground, where we have to replace steam vaults and steam piping with the appropriate stuff to move hot water around. But it also involves changing the heat exchange system on the inside of the buildings as well. The steam distribution stuff does not match up on a one-to-one basis with what we want inside the building for hot water. So it's an investment in the future. Now, it's an investment that's going to happen regardless, and that's true of so many institutions. And so much of the conversion to geothermal is nuanced in the same way. We already know the status quo is not good enough. We already know that we're not going to stay where we are. So we have to be careful that we're not comparing the cost of the future to the cost of today. It's an unfair comparison. We really need to compare the costs, whether they're the cost of building or the cost of operating a variety of future technological responses to our challenge. And once again, I think here, especially when we combine it with something like lake source cooling, deep geothermal has a really exciting opportunity to shift the needle about what decarbonization looks like.
Wonderful. So let's turn now to talk about Cornell's University Borehole Observatory, CUBO. So can you provide an overview of Cornell's CUBO project that was completed back in 2022 and what its primary objectives were?
Yeah, is that for me or for Burak? I can't remember.
Yeah.
I think it's for me. Okay,
Yeah.
sure. In 2022, the university drilled and completed a borehole just shy of 10,000 feet deep on campus. We've got, I think we're 9,781 feet total, about 2,000 feet of open section, and we're cased above that to the surface. It was a combination of a research project and a teaching opportunity and a data gathering exercise. And people often asked, well, what are you going to get from it? And one professor liked to say, the only thing that comes out of this well is information. And it has provided a lot of information. The idea was to appropriately categorize what is underneath our campus. What are the temperatures? What is the permeability? What is the rock strength? What's the drilling environment? What's the completion environment? What opportunities do we have? Is there pre-existing fluid in place? And Burak can answer more details, but the short answer is no. There's no easy button here. The solution is going to take careful, considerate, well-planned engineering and execution to pull it off.
Okay, so CUBO was just one observatory well. So now there is a current project. And so Burak, we're going to turn to you. Can you talk to us about the current project and the timeline and what the major findings are so far?
Sure. Actually, we have like two closely connected timelines in the horizon. And the first one involves actually what I'm just going to follow what Wayne said, deepening the existing CUBO well from 9,800 feet to 12,500 feet. And this is solely purpose of gathering additional data and finalizing for monitoring the future well pairs that we're going to supply heat to the campus. And the completion is going to involve installing the fiber optic cables, casing, and collecting more geophysical data that includes core samples, conducting geomechanical tests. And this deepening phase, we're aiming to start into 2026. And the second one, the well pair, is we're planning on drilling and testing their production by 2027. So we're looking at, a year or two from now, starting two major, milestones for Cornell. Now, what are the key discoveries? I think the major discovery is the temperature. So right now at 9,800 feet, we have approximately a temperature 990 Fahrenheit, which is 80 degrees Celsius. And this is suitable for deep direct use of the heat. And the another takeaway is, just like any other science, we need more data. So this is the second thing. And but for the audiences right now for the podcast, Cornell University has published multiple papers, and over the past 2 years, based on the existing findings, and they can refer to these papers for more detailed information. So this is how. What's my answers for this, the timeline?
Yeah, that's great. So are there particular results that you need to achieve with the first and second phase of CUBO to fully then implement the DDU at Cornell in 2027?
That's a very great question and a very tough question at the same time, because to fully implement the deep direct use, I think there's three main factors that will guide our decision making. One of them is the temperature, what's going to be there all long term, and the flow rate, and the long-term sustainability. So, at the surface, we're specifically aiming for a temperature range, something above 80 degrees Celsius, roughly, 170 to 212 Fahrenheit range, maybe above. And we're also aiming a flow rate over 50 kilograms per second. And at the same time, these are two simple constraints, but achieving these two is a highly interdisciplinary, task. This includes like many components to work, such as, subsurface water chemistry, how long it's going to take the reservoir to cool, and microseismicity, optimal well design. On the other hand, monitoring has to be also in place. So, I think particularly this is going to evolve once we have established the well pair. We're going to closely monitor how the subsurface conditions affect our temperature and flow rate, and how much heat that we can extract for a sustainable long-term objectives.
Okay, so I'm excited for this next question. I'm coming back to you, Wayne. So Cornell is looking at EGS, Enhanced Geothermal Systems. So can you talk a little bit about Cornell's preliminary concept for EGS reservoir development for deep district use? And then what are the benefits and challenges that are associated with EGS reservoir development?
Yeah, and Burak, you might feel like you need to step in when I miss something important. So Cornell is kind of we are really unusual as an educational institution in that we already have a borehole observatory on campus. And that means we have a drill pad on campus. So we intend to utilize that drill pad as a place that we already know how to permit it. We know all the logistics of running a drilling operation from that location. So we're going to use that for our next well pair. It's a fairly complex, highly deviated well pair that we have in design. We're going to be coming off that pad, and because we are constrained by the political boundaries of the university and our desire to design, build, and operate this first doublet wholly within the confines of our campus, the well design is much more complicated than it would be in a simple exploration and production arrangement. We actually we deviate and go nose down through vertical and come back underneath the borehole in the opposite direction, lined up with the minimum principal stress in our area. Its complexity adds cost. There's no doubt about that. It requires more expertise at every step of the program, including from the drillers. When we're done, we're going to end up with a pair of 21,000-foot wells with about 7,500 feet of parallel laterals, and they're going to be connected by a series of fracture stages. And the simple concept is to, for those of you who aren't geothermal practitioners, to inject cold water down one side of the well and extract hot water on the other side, remove the heat through a heat exchanger facility at the surface, and return the water through the injector.
Very exciting. So let's turn now to talk about what it's like executing this deep drilling project in an urban environment. And so, Wayne, I've got another question for you. What unique challenges does executing this project in an urban environment like the Cornell campus, how does this impact an institution like Cornell?
Well, Cornell is, I think, justifiably famous for being a beautiful campus in a really beautiful part of the country. We're situated on the hill overlooking a beautiful lake in a place that people spend a lot of money to come to spend their holiday time, their vacation time. So we treasure our local environment, and we value and respect everybody else's engagement and appreciation for that environment. And that adds complexity. There's no doubt. Everything about the project, from the route that you bring trucked materials in, to the hours of operation, to the type of sound that might be considered acceptable, to the impact on the immediate environment from emissions from how you provide power at your drill site, for example, are something that we consider. During the CUBO project, the Cornell team made the decision to power the entire drilling operation from our own electrical microgrid. And many people who came to visit the site said, this is the quietest drill site I have ever heard. Burak and I spend a lot of time thinking about all the different service lines that have to come to execute their critical aspect of this project, and how we can get them in, on site, through the job, and out with the smallest possible footprint. Because frankly, that's what our community requires of us. You know, the team that's worked for the years before I ever came to this project learned through, I think, through practice, through engagement, the value of listening to people, the value of really being a member of this community and hearing what people had to say, hearing if they have concerns, hearing if they have support, hearing if they have opposition, and putting all of that into the project planning. The CUBO that was built wasn't necessarily the CUBO that was envisioned at the beginning, but it was a really successful CUBO. And believe it or not, we actually had visiting hours during drilling where we had faculty members and members of the team there to answer public questions. And it was the kind of project where you could have visiting hours. And those of you who come from a drilling background know that is not common. We want to show the world that geothermal is this fantastic opportunity that takes this really unique skill set of people in the drilling industry, people in the completions industry, and takes that expertise and values it in a way that maybe it hadn't been valued before by a community that maybe had discounted it or hadn't fully understood its potential for impact. People like Burak, who spent years working in oil and gas drilling before becoming a geothermal driller, we could not do the work that we're doing without him. So we want to bring everybody in our community along with us in this very exciting process of creating a solution where right now we have a problem. And it's not easy to do that when we're on a campus surrounded by people who live there because it's a beautiful place, but it is something we can do.
I love that. That is such a great story. Chloe, I want to bring you into the conversation. Can you talk a little bit about how Cornell is navigating the complexities of drilling and then completing the wells in this area where there's no history of these types of projects?
Yes, thank you for the question. So as you all well know, usually drilling improves as you drill more wells because you gain knowledge of the site. Typically, you monitor parameters such as the weight on bit, the rounds per minute, or the injection of the mud. So the good news for us is that there is a little bit of history of the drilling part of the operation because CUBO was created on campus. And so we have some knowledge of the formation if we were to drill again. For instance, we learned that there are two potential areas that could be serving as reservoir. There are sedimentary rock, maybe between 8,700 feet and 9,400 feet deep, the Potsdam and the Galway formations that could be good candidates for a reservoir. The difficulty for that formation, as we learned, is that this is very hard rock, so very difficult to drill in. Below that depth, below 9,400 feet deep, there is the basement rock, which is also a very good candidate for a geothermal reservoir. The challenge here from a drilling perspective is that it's a highly heterogeneous rock, a very anisotropic rock, a rock that has discontinuities at multiple scales that we don't completely understand from a mechanistic point of view. But overall, we have a little bit of knowledge, and what is being done now at Cornell as we plan the next steps, I would say this is twofold. For one, there are really daily, weekly conversations with experts around the world who can advise on best practices for such formations. We have, thanks to Wayne and Burak, a very tight connection with the industry and practitioners who can advise us. And on the other hand of the spectrum, we do a lot of effort trying to use the data that is already there and plan some modeling work. We're trying to build some numerical simulators that would allow us to simulate the drilling itself, such that by sensitivity analysis and perhaps by machine learning tools, we might be able to optimize the process of drilling. So that's for the drilling part. Of course, the other aspect of your question was completion. What we learned through the process of drilling CUBO and analyzing the physical properties of the rock is that it is very unlikely that an EGS might work to produce a sufficient flow rate in an economically viable fashion unless we stimulate the rock. And so, of course, this requires a lot of preparation. So one of the things that's being done, again, is to work with practitioners who are working with us with the preliminary data that we have to produce models of what induced fractures might look like and how we might plan the work, how many clusters of fractures need to be there, according to the state of stress, what the orientation of the plane might be, and if there were a propping agent to be used, what would be the distribution of this propping agent? How can we optimize the conductivity of the fractures? So that is being done both from the data and the numerical simulation standpoint. Another thing that is already being done at Cornell is seismic monitoring. We do have a very extensive set of seismometers deployed in Ithaca around campus called CORNET that has been recording seismic activity before the construction of CUBO, during and after. It is still active today. It will still be active, and part of the current project is to even enhance the monitoring plan in order to understand where signals come from and come up with a go, no-go plan if any anomalous signal comes up from the measures. And I would say the last thing that we are navigating with is water, trying to minimize the use of fresh water to produce the fracture of network that we need to have in order to have an economically viable infrastructure. So again, this is done with experts in the field, and associated to that is the problem of treatment of water, of wastewater. By no means can we dispose of the water on site, so we are planning carefully on how to treat the wastewater in the most environmentally friendly possible manner. And I would say perhaps the last item on the list is air and air pollution, any methane leakage that might happen. And this is also something that Cornell takes very seriously. A lot of monitoring is being done, and we have the expertise on campus to even come up with some technologies to mitigate any form of detected natural gas that might occur. So these are the efforts that are currently being ongoing and envisioned to navigate a little bit of the uncertainty associated to these projects.
I'm impressed. Cornell seems to be very proactive in taking a lot of measures, which is very impressive. So Wayne, I want to come back to you with another question, and then Chloe, I do have some additional questions for you. But Wayne, what measures were taken during CUBO to ensure the project proceeded smoothly and safely?
Well, we talked about community engagement. There was a lot of community consultation. A committee was formed of sort of people with their fingers in a lot of community organizations who could communicate out and bring feedback back and advise us. That was really important. But then there's also, reaching out for expertise in the industry, like Chloe has said. Safety comes from people who do it every day. And those are the people who've they've seen what works in the field and they've formalized it and they have the ability to contextualize it. So in any situation where there was a variety of levels of safety that could have been established as the acceptable minimum, the highest was the one that was set in place. And the entire CUBO project, everything from day one of pre-mobilization site prep to down rigging the last piece of test equipment, and Burak and I were doing wireline with 9 Energy just a few weeks ago, was injury-free, accident-free, spill-free from A to Z.
Wonderful. Okay, so Chloe, I'm going to come back to you. I think we've got time for just a few more questions. I want to ask, in terms of research and teaching opportunities, so what are the benefits and opportunities when you're going to be drilling and completing, hopefully, this EGS well at Cornell?
So these are plentiful. If you imagine what the project might look like from the rig coming in to what it will look like when we operate this infrastructure. Think about the mechanics of wear and the design of materials to drill in harsh environments. It pertains to material sciences, to fracture mechanics and whatnot. Think about the mechanics of sequential hydraulic fracture propagation from a theoretical standpoint on how we understand fracture shadowing, how we model them also numerically. Think about non-isothermal multi-phase flow in a complex network of pores and fractures, and how we model this with equations and how we simulate those. Think about the assessment of the EGS system as a whole, as an energy system that encompasses not only the reservoir, but also the heat pumps and the district distribution system. The seismicity control, we talked about Cornell a little bit before, and by seismicity control, I'm talking about both the monitoring part of it, but also how we might be able to treat the site to avoid seismicity going forward. Some researchers are very interested in earthquake control. And so that's a kind of research question that we are talking about. In terms of computer science, think about the opportunity to have a digital twin on campus where you have a highly monitored site that informs you on the state of temperature, pore pressure, stresses, fracture openings, that you would feed into a model that would indicate what the next pressure, temperature, or stress might be at the next stage you pump water from your system. And think about the applied mathematics research in terms of stochastic partial differential equations, uncertainty management. And other aspects as well. We talked a lot about the engineering and the sciences, but think about the impact metrics. We're still not sure of how to calculate the impact of such technologies. First, because the impacts are not only for energy, but also for the environment and for society, but even for one aspect of it, which is perhaps what people have in mind most of the times when we talk about energy, the environmental impact. There's no full agreement on whether you should use an allocational method or a consequential method, or a combination of both, and which combination that might be. So there is ample opportunity to research on that and how it pertains to public policy and regulation. We still are in need of performant techno-economic analysis. This is also an area of active research. And then also associated with all this is the impact on sociological research and what it means to the communities to drill very deep in the earth. There is, in many communities, a sense of belonging to a place from a sense of belonging to the earth. And so the whole reflection associated with identity, land, and earth is also a very interesting one. And as we go in that route, there is also ample opportunity to go further in the research of the concept of trust in philosophy. What is public trust? And is it right or is it ethical to even understand the concept of trust? Because if you do understand and influence it, then this is not unbounded trust anymore. So this is the kind of research that is really interesting to look at. Associated to that is an opportunity for education and perhaps to have a well-rounded curriculum that would encompass most of the questions above. So if you think about engineering, of course, you're thinking about geomechanics, geophysics, geochemistry. You're also talking about energy systems. Again, this idea of not only understanding the heat pumps, but also the reservoir and vice versa, computational methods. As we move forward with more nonlinear problems, more complicated fracture patterns, more coupled processes, we need efficient models. We need to do what we call dimension reduction of the problem, understand the most pertinent variables of the problem, understand how to program and discretize equations in the most efficient way, in a more accurate way, in the most adaptive and agile way. Techno-economic analysis is a topic in itself that could be taught, public policy, ethics, sociology, and communication. And that's only for coursework. In terms of education through practice, we might think about internships and perhaps capstone design projects that would be in partnership between a faculty member and a member of different stakeholders, industry, government, or non-government organization. And lastly, there is ample room for creating an incubator on campus that would also bring in this idea of entrepreneurship, right? Where you are actually, you have all the tools at your disposal to train people to bring together the knowledge to implementation. And in order to do that, you really need to understand the science and the engineering, but you also need to be familiar and understand the regulation and the ethics part, right? And so I think that in the long run, what we're looking at is a true platform that would bring all that together, both to educate graduate students or perhaps convert the workforce from the fossil fuel industry to geothermal, or perhaps help people to implement a project that's almost ready to go, but for which counseling is needed.
That is so impressive that you're able to pull that many opportunities for teaching and internship. I'm just so impressed that this geothermal project is bringing all of that to the table. Wow, so there's a lot of impact that Cornell is going to have on the industry with just this project. So how do you see, this is my last question, that this project is going to impact the future of renewable energy in North America?
So I think that the unicity of this project is that what we aim for here is a prototype EGS in the northeast of the United States in particular. It has a specific geology associated to it and its specific challenges. So the very fact that such a prototype would exist is already very impactful because it will bring a lot of knowledge on the technical, logistical, and socioeconomic challenges that might exist. In addition to that, by doing it, we're going to learn more about the problem, perhaps not have the full solution, but have some constraint on the best solutions. Meaning by that, we will identify the variable parameters of the problem and perhaps the main constraints of the problem and provide some recommendations for best practices. I think another outcome and impact for the community will be to have a truly interdisciplinary team at work. And when I say interdisciplinary team, I'm talking about professors in public policy, in philosophy, in earth science, in engineering, as well as engineers like Burak and Wayne, together with external stakeholders, including our local government, some industry partners, and non-government associations as well. And so having a model for which that we can follow in order to bring together so many people with so many backgrounds that are so passionate that they can work together on a long period of time for a project that is high risk, by itself also is an achievement and can have a lot of impact. In general, what we want to achieve is a fully operating EGS that would produce direct heat on campus and a research institute that would provide a platform for research, education and incubation on campus, which of course would have a huge impact in the Northeast and in the country in general. In the long run, my personal belief is that if we're successful in achieving this prototype and this EGS, we will bring more energy independence to this country and more participation of local communities in local infrastructure for energy. And lastly, perhaps more importantly, hope that EGS can bring a more sustainable and equitable source of energy.
This is so exciting. Well, I'm going to be eagerly watching you guys and what you're doing at Cornell, and just super excited for the years to come with your project. I want to thank each of you for joining me today, and I want to thank our listeners for joining us on this episode of Geothermal Unleashed. I hope today's discussion has sparked new insights and deepened your understanding of the geothermal industry's incredible potential. Until next time, keep pushing the boundaries of what's possible, and let's continue working together to unleash the full potential of geothermal. Thank you.